Hello everyone, a very good evening to all. Uh, I welcome you all once again for this 11th interaction session on Atomic and Molecular Physics course, which is being taught this semester by NPTEL with course code NOC25PH04. So, myself, Vivekananda Nayak, I am a PhD research scholar in the Department of Energy Sciences and Engineering, Plasma Physics Laboratory, IIT Delhi. So, today we will be discussing a few sample problems that will be based on the week 11 the on the lectures of week 11 of the course. So this week's lecture was mainly about the electronic spectra and the intensity of vibration electron spectra. For example, the principle which governs the intensity, it is the Frank-Condon principle that was also discussed. So we will first discuss briefly some of the concepts and then we will go on to discuss the problems. So we know in case of molecular spectra corresponding um, in addition to electronic spectra there are other spectra due to the relative motion of the two atoms that are present in a molecule. So one is rotational spectra, one is vibrational spectra, and the third one is electronic spectra. So if you talk about different order of energy, suppose for convenience we will be representing in terms of wave number units. So the energy difference in rotational is of the order of 10 to the power minus 1 centimeter inverse. 1 minute. Then for vibrational spectra, delta E vibration equals to 10 to the power 3 centimeter inverse, the order of energy. And similarly for electronic spectra, the energy is again higher. Electronic delta E electronic of the order of 10 to the power 5 centimeter inverse. So if you talk about the total energy, so total will be delta E electronic plus delta E rotational plus delta E vibrational. And if you talk about the spectra, pure rotational spectra, is exhibited by the molecules which have a permanent dipole moment. Molecules having permanent dipole moment, and they are called as microwave active or inactive molecules. For example, HCl, NaCl, CO, they are microwave active because they have permanent magnetic dipole moment. However, for CCl4, H2O2, CO2, all these they are inactive as they don't possess dipole moment. And if we talk about the vibrational spectra, then vibrational spectra are shown by the molecules that have uh, uh, for which there is change in dipole moment during motion. So for vibrational spectra, change in dipole moment during motion. For example, HCl, NaCl, carbon monoxide, CCl4, CO2, they are infrared active, but H2O2, Cl2, I2, they are inactive. So here you can see there are a few molecules. Those doesn't possess rotational spectra, but they show vibration spectra. For example, CCl4, CO2, because they don't have any permanent dipole moment. However, during motion there is change in dipole moment. However, if you talk about electronic spectra, all molecules exhibit electronic spectra because it depends upon the electronic distribution. And we know electrons are distributed in different molecular orbits according to their energy values, and corresponding to which we have molecular in electronic spectra. So all the molecules they show electronic spectra, but some of the molecules that doesn't show rotational spectra or vibrational spectra. And if we talk about the intensities of spectral lines, it is governed by Frank-Condon principle. And what Frank-Condon principle says, Frank-Condon principle, basically it says electronic transition occurs so rapidly that in comparison to the change in interatomic distance and in intensity of maximum spectral line of transition occurs only when the transition so the intensity of spectral line is maximum when the transition occurs from bottom to bottom. So for example, suppose this is a level, and these are two levels. You know, in case of molecule the electron levels are done like this due to the interaction between the two nucleus, so that it has a minima. So suppose there are two levels, this is R, and corresponding to, suppose this is ground state and this is excited state. So suppose corresponding to each ground state there are different levels, and corresponding to excited state there are also different levels. With respect to the transition for which the levels involved are bottom levels, they will be having maximum intensity. For example, suppose this is bottom to bottom, this is one transition, this is another transition, this is another, this is another. So this transition will be having maximum intensity spectral line, and then there will be other lines corresponding to other transitions. So Maximum intensity occurs only when the transition occurs from bottom to bottom. So intensity is maximum when transition occurs from bottom to bottom. And another most important thing is, it also says that the electronic transition occurs so rapidly that there is no change in interatomic distance. That is, the time scale of the electron transition is so rapid in comparison to the change in interatomic distance. So the interatomic distance remains fixed or remains constant during the electronic transition in a molecule. So with this, we will be now solving a few problems that will be based on the concepts of the week 11 lectures, which basically covers vibrational electronic spectra, rotational spectra, all these things. So coming to the first question of today's interaction session, the question says the fundamental uh, band for carbon monoxide is centered at 2143 centimeter inverse, and the fast overtone is at 4260 centimeter inverse. And from these data, we need to calculate the anharmonicity term, that is omega e xc. So the question says the fundamental band for carbon monoxide is centered at 21.43 centimeter inverse and fast overturn at 42.60 centimeter inverse. Then we need to find out the anharmonicity, that is the product of omega e and xc. The options are option A 13.45 centimeter inverse, option B 13 centimeter inverse, option C 12.5 centimeter inverse, or option D 14 centimeter inverse. So I'll give you a few minutes to think about this question, and then we will discuss what will be the correct answer. So, if we discuss, the question was the fundamental band for carbon monoxide is at 2143 centimeter inverse, and the fast overturn is at 4260 centimeter inverse. Now, we have to find out what are the transitions that are called as fundamental transition and what are the transitions that are called as fast overturn transition. So, here we are talking about vibrational spectra, because in vibrational spectra there is anharmonicity, because the vibration of a molecule is considered as the motion of a simple harmonic oscillator, but there are some anharmonicity, and those anharmonicity is introduced in terms of additional term. So if you talk about the expression for vibrational energy, so if you add the anharmonicity term, then it will be V plus half Hc omega e, that is in terms of vibrational constant, minus V plus half square Hc omega e xc, where omega e xc is the anharmonicity. Now, and this omega e is called as vibrational constant. Now, if we express in terms of wave number, because in question all the values are given in terms of wave number, so if we convert in terms of wave number, so so if you apply, so this will be the formula. Then the fundamental frequency corresponds to V0 to V1, and fast overturn will be V0 to V2. So you can use these values and you can calculate the value of omega xc. So I'll give you a few minutes to try this and then we will discuss. I'll be back in a few minutes. So if we talk about the transition for this fundamental frequency and then fast overturn. So for fundamental frequency, so if you do it, it will be, so let's write the delta GB. So delta G, it will be omega E V prime plus half minus omega E x E. So if we convert it E in terms of wave number unit, so it will be GB, which is equals to E by HC. It will be V plus half omega E minus V plus half square omega E xc. So we are using this formula here. So delta GB will be omega E V prime plus half minus omega E xc V prime plus half square, then minus omega E V plus half plus omega E xc V plus half square. So in case of fundamental, V prime is 1, V is 0, and in case of fast overtone, V prime is 2, V is 0. So for fundamental, if you calculate your delta GV, so delta GB, it will come out to be omega E minus 2 omega E xc, omega E minus 2 omega E xc, because here you see it will be V prime will be 1, so 1 plus half 3 by 2, and here it is 0. So 3 by 2 minus half, it will be only omega E, and then here it's minus omega E xc. So here it will be 1 plus half 3 by 2 square, which is 9 by 4, minus or plus 9 by 4 plus this will be 1 by 4. So 9 by 4 minus 1 by 4, it will be 8 by 4, which is 2 omega E xc. So this is for fundamental. Similarly, for fast overturn, if you calculate where V prime equals to 2 and V equals to 0, then your delta E, so delta GV, it will be 2 omega E minus 6 omega E xc. This is equation 2. So now this, from the question we have this for fundamental band it is 2143, and for fast overturn it is 4260. So from the data given, we can write 2143 is equals to omega E minus 2 omega E xc, and 4260 equals to 2 omega E minus 6 omega E xc. So if we multiply 2 here and then we subtract it, this will cancel each other, and if you calculate, this will be 6 omega E xc minus 4 omega E xc equals to 2143 into 2, which is 4286 minus 4260, which is 26. That implies 2 omega E xc is 26, and omega E xc is equals to 13 centimeter inverse. So this is the answer, and the correct option will be option B, 13 centimeter inverse. So in order to get the value of omega E xc, there are two conditions. One was for fundamental band of frequency, and another was for fast overturn. So we put the conditions of transition, that is the value of V prime and V for those two transitions, and then we got the correct answer. So now we will move to question number 2. So question number 2 says the displacements from the exciting lines in a rotational Raman spectra of HCl are represented by delta nu is equals to plus minus 62.4 plus 41.6 J centimeter inverse. Then find the moment of inertia of HCl molecule. The options are option A 2.7 into 10 to the power minus 47 kg meter square. Option B 1.05 into 10 to the power minus 44 kg meter square. Option C 2.7 into 10 to the power minus 40 kg meter square, or option D 3.5 into 10 to the minus 45 kg meter square. So we need to find the moment of inertia, and it is given that in the exciting lines in rotational Raman spectra, it is represented by this expression. So this question is based on Raman spectra. So first we need to know what will be the expression for this displacement in case of rotational Raman spectra, and then by comparing we can calculate the moment of inertia of HCl molecule. So we will be discussing after a few minutes. So you first think how we can approach this problem and solve it, and then we will discuss. So if we discuss about rotational Raman spectra, so in case of rotational Raman spectra, we know in case of a rigid rotator, the energy is given by Ej equals to J into J plus 1 bhc. Now for rotational Raman spectra, for rotational Raman spectra, delta J is equals to plus minus 2. So if you um, check the if you check the expression for wave number of transition, then it will come out to be 4 J plus 3 by 2 B. So we can write it as 2B into 2J plus 3. So this is the expression for the wave number in case of a rotational Raman spectra. Now, if you see the question, it is given as 62.4 plus 41.6 J centimeter inverse. So now if you compare 4B J plus 3 by 2, it is equal to 41.6 J plus 62.4 divided by 41.6. So 41.6 J plus, if you uh, calculate it, it will be 3 by 2 only, 3 by 2 centimeter inverse. Now comparing what we get 4B is equals to 41.6 centimeter inverse. That implies B is 10.4 centimeter inverse, or in terms of meter inverse it will be 1040 meter inverse, because in the question the moment of inertia is expressed in terms of kg into meter square, so we need to convert the wave number unit into meter inverse rather than in centimeter inverse. So this is B, and we know the expression for B, that is the rotation constant, is given by h by 8 pi square IC, where I is the moment of inertia, moment of inertia. So what will be the value of I? The value of I will be h divided by 8 pi square BC. So if you put the values, h is 6.626 into 10 to the power minus 34 divided by 8 into 3.142 square. B is 1040 into C is 3 into 10 to the power 8. If you calculate it, you will get 2.689 into 10 to the power minus 47 kg into meter square. And if you see the options, so the closest option is 2.7 into 10 to the minus 47 kg into meter square. 2.7 into 10 to the minus 47. So which is 2.7 into 10 to the power minus 47 kg into meter square. So the correct option will be option A. So basically this question was related to rotational Raman spectra, and the expression for the transition the wave number, uh, the expression for the wave number of transition is given by 4b j plus 3 by 2, and if you compare it to the given expression for the wave number, we found that 4b is 41.6 centimeter inverse. So B will be 1040 meter inverse. Then from the expression for B, from the expression of B, we can calculate the value of moment of inertia, and the moment of inertia is 2.7 into 10 minus 47 kg meter square. I hope this is clear to everyone. Now we will move to question number 3. Question number 3 says a diatomic molecule has vibrational states with energies. The expression for energy is EV is equals to h cross omega V plus 1 by 2, and the rotational energy state with energies Ej is B j into j plus 1, where V and j are non-negative integers. Consider the transitions in which both the initial and final states are restricted to V less than equals to 1 and j less than equals to 2, and subject to the selection rules delta V equals to plus minus 1 and delta j equals to plus minus 1. Then the largest allowed energy transition is, options are option A h cross omega plus B, option B h cross omega minus 4B, sorry, plus 4B, h cross omega minus 4B, and option D is 2 h cross omega minus B. So here the vibrational state expression is given, the rotational states expression is given, and the conditions here given is that consider those transitions in which both initial and final states are restricted to V less than equals to 1 and J less than equals to 2. And the selection rule is delta V is equals to plus minus 1, delta is equal to plus minus 1. Then what will be the allowed energy of transition? We need to find out. So I'll give you a few minutes to think about this question, and then we will discuss. So if we discuss the vibrational level has the expression, so E vibration, it is h cross omega v plus half, and E rotation, it is b j into j plus 1. So E total is E vibration plus E rotation, which is equals to h cross omega v plus half plus b j into j plus 1. So what will be delta E? Delta E will be, for delta E the transition occurs from v prime to v, j prime to j. So the expression for delta E will be h cross omega v prime plus half plus b j prime into j prime plus 1 minus h cross omega v plus half plus b j into j plus 1. Then delta U will be h cross omega v prime minus v plus b j prime square minus j square plus j prime minus j. So we can write it as h cross omega delta v plus b, this j prime a square minus b square, if you apply, it will be j prime plus j into j prime minus j. It will be j prime plus j into j prime minus j plus j prime minus j. But here the conditions, what are the conditions given? Delta v is plus minus 1, delta j is plus minus 1, and v should be less than equals to 1, and j will be less than equal to 2. So what are the transitions? So here we can put delta b equal to 1, and then for delta j it is plus minus 1. So here it is given j is less than equals to 2, so we can put j prime equals to 2 and j equals to 1, because only then it will satisfy the condition that any of the, because in the question it is given both the initial and final states are restricted. So if you restrict the values of initial and final states of j, so maximum value is 2, so j will, j can't be 0. So sorry, if you put the value of j, it will be 0, so maximum is 2, so it will be 2, j prime will be 2 and j will be 1. So if you put all these values, then what will we get? Delta E will be h cross omega into 1 plus b into j prime plus j, it is 3, 3 into 1 plus 1, so it will be h cross omega plus 4b. Because here see the question says what is the largest allowed energy transition. So since you need the largest value of energy transition, that's why we are taking j prime equals to 2, because j prime equals to 1, it will be having less energy. So if the level involved has maximum j value, then energy will be maximum. So in that case, we are taking j prime equals to 2. So this is the correct answer. So delta E will be h cross omega plus 4b. So the correct option is option B, H cross omega plus 4b. I hope this is clear to everyone. Now we will move to question number 4. Question number 4 says, in carbon monoxide molecule, the J equals to 0 to J equals to 1 absorption line occurs at frequency of, options are option A 1.23 in 10 to the 12 Hz, option B 1.15 in 10 to the 11 Hz, 1.07 in 10 to the 13 Hz, or option D 2.52 in 10 to the 11 Hz. So it says in case of carbon monoxide molecule, the J equal to 0 to J equal to 1 absorption line. We need to find out the difference in energy when the transition occurs from J equal to 0 to J equal to 1. Then corresponding to that, we can calculate the frequency of that transition. So these are the options. I'll give you a few minutes to think about this question and then we will discuss what will be the correct option. So if we discuss, we know when the transition occurs for J0 to J1, then delta nu bar from 0 to 1, it is 2b, and in terms of energy, delta E transition from 0 to 1, it will be 2b hc, because the expression is j into j plus 1. So Ej is j into j plus 1 hc. So j1 is 1 into 2, j1 j0. So it will be 2b HC minus 0, which is 2B HC. So, and we know B will be H by 8 pi square I into C. So now 2BHC is equals to delta E, which is H nu. That implies nu will be 2B into C. So now first we need to find out the value of B. So what is the value of B? B will be H divided by 8 pi square I C. So if you calculate the value of B, because we have the moment of inertia 1.46 into the power minus 46. So H is 6.626 into 10 to the power minus 34 divided by 8 into 3.142 square into I is 1.46 into 10 to the power minus 46, 1.46 into 10 to the power minus 46 into 3 into 10 to the power 8. So if you calculate, we will get it will 191.6 meter inverse. So now if you put the value of B, so frequency is 2 into 2B into C. So 2 into 191.6 into C is 3 into 10 to the power 8. It will be 1149.6 into 10 to the power 8, or if you see the options are in 11 or 12, 10 to the power 12 or 10 to the power 11, it will be 1.1496 into 10 to the power 11 hertz, or it will be 1. If you see the options, it is 1.15, it is present in the option. So 1.15 into 10 to the power 11 hertz. So in the question it was given that the absorption line occurs at frequency. So this is the value of moment of inertia for carbon monoxide. So for that value we can calculate B. Then corresponding to the transition from J equal to 0 to J equal to 1, we know the expression is 2B for the wave number. So the frequency will be 2BC. So if you put the values after calculating the value of B, you will get the frequency is, this is the frequency, which is 1.15 into 10 to the power 11 hertz. I hope this is clear to everyone. Now question number 5. Question number 5 says the fast absorption spectra of C12O16 and C13O16 are respectively at 3.842 centimeter inverse and at 3.673 centimeter inverse. Then what is the ratio of magnetic moments of C13O16 to that of C12O16? So actually this is not magnetic moment, this is moment of inertia. This is moment of inertia, because here there are isotope effects are present here, because it is in one case it is C12 and another case it is C13. So here we need to find out the moment of inertia, because moment of inertia contains the reduced mass, and reduced mass depends upon the mass of the atoms present in the nucleus. So in since in both the molecules carbon has different mass, so there will be some change in the mass, and due to that there will be some change in moment of inertia. That's why the fast absorption spectra is coming at different positions. That is, for one case it is 3.842 centimeter inverse, and for other case it is 3.673 centimeter inverse. So the options are option A 0.98, option B 1.032, option C 0.79, or option D 1.046. So I'll give you a few minutes to think about this question, and then we will discuss what will be the correct answer. So if we discuss now, we know the value of energy Ej is J into J plus 1 B, where J is 0, 1, 2, 3 like that, and the value of B, it is H divided by 8 pi square IC. So B is inversely proportional to I, where I is the moment of inertia. So if we talk about the expression, so delta F, delta E, we can say J, it will be E for J plus 1 minus E for J. So it will be B J plus 1 into J plus 2 minus B J into J plus 1. So this is the expression. So if you calculate, it will, so B, it is J plus 1 is common, so J plus 2 minus J, it is 2B J plus 1. So for J equals to 1, from J equals to 0, this delta Ej, this is 2B, 0 plus 1, that is 2B. However, if you see, one is C12O16, C12O16, and it is, the value is 3.842 centimeter inverse, 3.842 centimeter inverse, and for C13O16 it is 3.673. C13O16. So the energy change for J equal to 0 to J equal to 1 transition, because here the it is given as fast absorption spectra. So for fast absorption spectra, the transition is J prime to J 1 to 0. So for C12O16 divided by delta E C13O16, it is 2B for C12O16, 2B for C13O16. However, we know this B is inversely proportional to B. So B is inversely proportional to the moment of inertia. So it will be, so this, it is given, it is 3 point. So for C12 also it is 3.842 divided by 3.673 is equals to C3. So it will be moment of inertia of C13O16 divided by moment of inertia of C12O16. So here you see B. Here in the previous case where we are writing B, so in the numerator it was C12O16, but here since B is inversely proportional to moment of inertia, so it will be C13O16. So if you calculate, so I for C13O16 and I for C12O16, it is 3.842 divided by 3.673, it is 1.046. So the correct option is option D. This is the this is the correct answer. That is the in the question it was the ratio of moment of inertia of C13O16 to that of C12O16. So the ratio of inertia is 1.406. I hope this is clear to everyone. Now we will move to question number 6. So question number 6 says, which of the following molecules produces vibrational spectra but not rotational spectra? Options are option A HCl, option B CCl4, option C carbon monoxide, or option D NaCl. So if you remember, we are discussing at the beginning of the today's interaction session that there are some molecules that show vibrational spectra because for those molecules they have no, they are called as infrared active, and for those molecules they show rotational spectra, they are called as microwave active molecule, and for rotational spectra the molecule should be having permanent dipole moment. However, for vibrational spectra there should be change in dipole moment during motion. So if you see the molecules that doesn't show rotational spectra, so because so no rotational spectra, it means no permanent dipole moment. If you talk about HCl, it has permanent dipole moment. For carbon monoxide, it has permanent dipole moment. For NaCl, so they all have permanent dipole moment. So the correct option will be option B, that is CCl4. So CCl4, it produces vibrational spectra but not rotational spectra because it is so all carbon is bonded to chlorine from all sides, so it is a symmetric structure. So there are no permanent dipole moments. That's why it doesn't show any rotational spectra. However, it shows vibrational spectra. So CCl4, no rotational spectra but shows vibrational spectra. Now we will move to question number 7. Question number 7 says the molecule hydrogen fluoride has an absorption line in the rotational band at 40 centimeter inverse for the isotope fluorine 18. Then the corresponding line for the hydrogen fluoride for isotope fluorine 19 will be shifted by an amount of, options are option A 0.12 centimeter inverse, 0.22 centimeter inverse, option C 0.16 centimeter inverse, or option D 0.18 centimeter inverse. So again, this question is related to the rotational band. Since there are isotopes, so this question is related to isotope effect. And what is isotope effect? Because the rotational spectra, which is expression h by 8 pi square IC, it is inversely proportional to I, which contains reduced mass. So isotope effect comes into picture. So now we need to find out what will be the value of shifted line corresponding to the isotope fluorine 19. So I'll give you a few minutes to think about this question and then we will discuss. So if we discuss, so first we need to find out the value for b. So here it is given at the in the absorption line in the rotational band, it is 40 centimeter inverse. So we know uh, the transition from the fast absorption line corresponding to transition from j equal to 0 to j equal to 1, and the value of the transition delta E is 2b. So it is 40 centimeter inverse. So B is 20 centimeter inverse for F18. So now we need to find out the value of B for F19. So how we will find out? You know B, it is h by 8 pi square IC, or B is inverse proportional to I. Now I is mu c square, so you can direct write B is inverse proportional to 1 by mu. So all remaining are the same. So if we want to find out the same shift or the same line corresponding to corresponding to F19, then we need to find out what will be the value of mu for F19. So for HF where 1 and this is 18, so it will be 18 into 1 by 18 plus 1, but the mu for HF where H1 and F19, it is 19 into 1 by 19 plus 1. So now if we talk about the value of B2 by B1, where B2 is for HF H1 F19 and B1 is for H1 F18, then B2 by B1, it will be equal to mu1 by mu2. That implies B2 will be mu1 by mu2 into B1. So B2 equals to B1. B1 is 20 into mu1. Mu1 is 18 into 1 by 18 plus 1. 18 into 1 divided by 18 plus 1 into mu2 divided by mu2. So into it will be 19 plus 1 divided by 19 into 1. It will be 20 into 18 by 19 into 20 by 19. So if you calculate, it will come out to be 1994 19.94 centimeter inverse. Now since it is 1994 centimeter inverse, so for H1 F19, the transition or the corresponding to the transition from j equal to 0 to j equal to 1, it will be 2b2. It will be 2 into 19.94. So it will be 39.88 centimeter inverse. So now the shift, it will be 2b1 minus 2b2 will be 40 minus 39.88, which is 0.12 centimeter inverse. So the correct option will be option A, 0.12 centimeter inverse. I hope this is clear to everyone, because in this question it was the absorption line corresponding to the rotational band of HF, where F18 was present, it was 40 centimeter. Then we need to find out the shift for the same band at for the same band for F19. So due to the difference in mass, there will be change in the rotational constant, and that's why there will be change in the position of the line. So if you calculate it will be B1. So B1 was 20 centimeter inverse. It was for H1 F18, and the expression for B is H by 8 pi square IC. So it is inverse proportional to I, and since moment of inertia is direct proportional to the reduced mass, so again B is inverse proportional to 1 by mu. So that's why B2 by B1 will be mu1 by mu2. For mu1, this is mu1 HF18, it is 18 into 1 by 18 plus 1, and mu2, it is HF19, 19 into 1 by 19 plus 1. So if you calculate, the value of B2 will be 19.94 centimeter inverse. So now, similarly, since the shift is 2B, so it will be 2B2, that is 39.88 centimeter inverse. So if you calculate the actual shift, it will be 40 minus 39.88, which is 0.12 centimeter inverse. So I hope this is clear to everyone. And now we will move to the next one. Question number 8. Question number 8 says the observed wave number, that is 1 by lambda, in a vibrational spectra corresponding to the transition V equals to 1 to V equals to 2, where V is the vibrational quantum number, in terms of vibrational constant omega, that is nu by c, is where it is given that not required to consider any anharmonicity. So we will not consider any anharmonicity, we will consider the simple harmonic motion. The options are option A half omega, option B omega, option C 2 omega, and option D 3 by 2 omega. So if we see here, we know the vibrational level is given by V plus half h nu or h cross omega. We know h, so this is hc by lambda is equals to h nu V plus half. So 1 by lambda is equals to nu by c V plus half. And here nu by c is given, it is omega, so it is omega V plus half. So 1 by lambda is omega V plus half, where it is in meter inverse or length inverse unit. So here the says that here it says the transition from V1 to V2. So transition from V equals to 1 to V equals to 2. So 1 by lambda from V2 to V1, it will be omega V prime plus half minus omega V plus half, where V prime is 2 and V is 1. So 1 by lambda will be omega 2 plus half minus omega 1 plus half. So it will be omega 5 by 2 minus 3 by 2. It will be omega. So the wave number or the observed wave number corresponding to transition between V equal to 1 and V equal to 2 is omega, that is option B is the correct one. I hope this is clear to everyone. It was a pretty much simpler question as compared to the question that we have been solving throughout the day. So now this is question number 9. So question number 9 says find the vibrational energy of carbon monoxide molecule for vibrational quantum number B equals to 2. Given the force constant of the bond in CO is 1870 Newton per meter and the reduced mass of CO is 1.14 into 10 to the power minus 26 kg, and the value of Planck's constant is also given, it is 6.627 into 10 to the power minus 34 joule into second, and the options are option A 106.84 into 10 to the power 21 joule, option B 34.08 into 10 to the power minus 19 joule, option C 205.35 into 10 to the power minus 22 joule, or option D 14.54 into 10 to the power minus 23 joule. So this question related to find out the value of vibrational energy for carbon monoxide molecule, and the data are given and we need to find out what will be the correct option. So if we discuss, we know the frequency of oscillation in case of a molecule. If you assume the simple harmonic oscillation or simple harmonic motion, the frequency is given as nu equals to 1 by 2 pi k by mu root over, where k is called as the force constant and nu is called as the reduced mass. So the reduced mass mu for carbon monoxide is given. It is 1.14 into 10 to the power minus 26 kg, and the force constant k is also given. It is 1870 Newton per meter. So now also the value of Planck's constant is given. H is 6.626 into 10 to the power minus 34 joule into second. So now if you calculate what will be the value of frequency, the value of frequency will be 1 by 2 pi 1870 divided by 1.14 root over into 10 to the power 13 hertz. Because here this minus 26, it goes to the numerator and it will be the square root will be 26, so it will be 13. It is 40 divided by 2 pi into 10 to the power 13. It will be 6.45 into 10 to the power 13 hertz. And now if we talk about the energy, we know energy for V equals to 2, it will be h nu V plus half, that is h nu 2 plus half, or 5 by 2 h nu. So E will be 6.626 into 10 to the power minus 34 into nu is 6.45 into 10 to the power 13 into 5 by 2. So if you calculate, it will come out to be 106.84 into 10 to the power minus 21 joule. So which is the correct answer. So from the given value of reduced mass and force constant, we calculated the value of frequency, and using the value of frequency, we put when we put the value of frequency in the expression for energy, because the energy is h nu v plus half, and for v equal to 2, it is given in the question for vibrational quantum number v equals to 2. So if you put v equals to 2, it will come out to be 5 by 2 h nu. So the correct answer will be 106.84 into 10 minus 21 joule. So I hope this is clear to everyone. Now we'll move to the question number 10, which is the last question of today's interaction session. And it says, assume that the H2 molecule behaves like a harmonic oscillator having force constant of 575 Newton per meter, and find the vibrational quantum number corresponding to the energy 3.936 into 10 to the minus 19 joule, given that the reduced mass of hydrogen molecule is 8.35 into 10 to the minus 28 kg, and the value of Planck's constant is 6.626 into 10 to the minus 34 joule into second. So this question is pretty much similar to the previous question, but in previous question the quantum number v was known to us and we calculate the energy. Here the value of energy is known to us and we want to calculate the value of the quantum number. So options are option A 2, option B 4, option C 6, or option D 8. So if we solve this one, so similar to the previous question, we know nu it is 1 by 2 pi k by mu root over, it is 1 by 2 pi k is 575 divided by mu is 8.35 root over into 10 to the power 14, and if you calculate it, it will come out to be 1.32 into 10 to the power 14 hertz. Now this E is h nu B plus half vibrational energy level, so this E, which is h nu into V plus half, this is equal to the energy is given to us 3.936 into 10 to the minus 19. 3.936 into 10 to the power minus 19. So h nu into V plus half equals to 3.936 into 10 to the power minus 19. V plus half is equals to 3.936 into 10 to the power minus 19 divided by 6.626 into 10 to the power minus 34 into frequency is 1.32 10 to the minus 4, 1.32 into 10 to the power 14. So if you calculate, it will be 3.936 divided by 1.32 into 6.626 into 10 to the power minus 19 into 10 to the power minus 14 into 10 to the power 34. So if you calculate, it will come out to be roughly 4.5. So V plus half is 4.5. It implies V is 4.5 minus half, 4.5 minus 0.5, which is 4. So the value of vibrational quantum number is 4. So this question was pretty much similar to the previous question, but here the only unknown was the value of vibration quantum number. So first we calculated the value of frequency, and then by using the value of frequency we calculated the value of vibrational quantum number V. So V plus half was 4.5, so V is 4. I hope this is clear to everyone. With this we come to the end of today's interaction session. So in the next interaction session, which will be the which will be based on the lectures of week 12. So in that interaction session, we will discuss about Raman spectroscopy and how the spectral lines and their problems will be solving, which will be based on the concept of Raman spectra. And there will be another interaction session that I will take on the next Tuesday, but because the 12th interaction session will be on next Monday, that is 14th, I guess, exactly 14th. And then on 15th, I will be taking another interaction session, which will be from 7:30 p.m. to 8:30 p.m. And in that interaction session, I will be giving an overview of the whole concepts that has been taught in this atomic and molecular physics course, and that will be really helpful for you for your exam preparation. That will be some sorts of revision of the concept that we have been studying throughout this course. So with this, I end this interaction session. That's it from my side. Thank you.